Howdy, howdy, this is Mr. Potter. We're going to be starting with Chapter 5 now, so we're going to be dealing with another aspect of functions. And what we're going to be talking about in today's lesson is we're going to be talking about a Riemann Sum approximation. The main idea behind this is that we're going to be looking at areas under a curve. So let's say that I have y equals x squared. So I know that this is a parabola. But if I'm only looking at what's happening, say, on the domain from 0 to 3, I'm going to have this part of my parabola at 1, at 2, and at 3. And I want to talk about what I can determine about the area under this curve. So I'm looking for this area here. And it's not easy to determine what it is, but what I can do is I can use rectangles to determine this area, at least get a good approximation of it. The question is, how do I set up my rectangles for this? I could set up my rectangles where I'm dealing with the right endpoint of a curve, or I could be dealing with rectangles where I'm dealing with the left endpoint of a curve, or I could be dealing with the midpoint and determining the area based on that. There are three different ways of looking at these rectangular approximations, but all of these come through the mathematician Riemann. He was one of the first ones who talked about how to approximate the area under a curve by using rectangles. And so I want to deal with this situation where I have y equals x squared, but I'm going to be looking at it from a left Riemann sum. So in other words, when I'm looking at this on the domain from 0 to 3, I'm looking at the area under the curve. I'm looking at it where my data points are going to be data points on the left edge of my domain. So from 0 to 1, I'm using the left endpoint, and I actually have an area of 0 here. For this rectangle, I'm using it from 1 to 2 with a height of 1, and so my area is 1. And for this rectangle, I'm looking at an area where the height is 4 and my base is 1, so my area is 4. So I'm looking at this, and if I'm approximating using these left rectangles, where the height of my rectangle is determined by the left endpoint, then my area is approximately 0 plus 1 plus 4, or an approximate area of 5 square units. Now I'm looking at this, and this is obviously an underestimate, because I'm certainly ignoring all of this area here. And so maybe a left Riemann sum is not the best Riemann sum to look at for this curve. Maybe I want to do my rectangles using a right Riemann sum. So looking at the exact same function, y equals x squared, on my exact same domain from 0 to 3, but instead looking at the right endpoints instead of the left endpoints, then what happens is this right rectangle is going to have its height determined by the right endpoint, a height of 1 and a base of 1, so my area is 1. Here, this rectangle is going to have its height determined by the right endpoint from 1 to 2. So that's a height of 4 and a base of 1, so here my area is 5. And here, my right endpoint determines a height of 9, and so the area of this rectangle is 9. So my Riemann sum approximation for the right would be 1 plus 5 plus 9, which is 15. And this is pretty clearly an overestimate, because I'm certainly including area that was not in my original graph. So the thing is, a left Riemann sum and a right Riemann sum have its difficulties, because I'm either going to be including area that I don't want, or I'm going to be excluding area that is actually part of my curve. But Riemann also came up with the notion of using a midpoint Riemann sum approximation. In other words, if I have y equals x squared and I'm looking at this parabola again, I'm still going to partition it exactly the same way, but I'm going to let the midpoint of each one of these intervals determine the height of my rectangle. In other words, when I'm at x equals 0.5, that determines a height of 0.5 squared. And so here this area would be 0.25. When I'm at x equals 1.5, my height is going to be determining, my area is going to be determined by a height where the height is 2.25, and so here my area is 2.25. And if I'm looking at an x value of 2.5, the height of my rectangle is determined by this midpoint squared. 2.5 squared is 6.25. And so my area approximation using this midpoint Riemann sum would be 0.25 plus 2.25 plus 6.25, or 8.75. Now this does have an added benefit for us. Notice that in each one of these rectangles there's areas that I'm ignoring, but there's also areas that I'm including. And of course the notion here is that this positive area and this negative area really should kind of cancel each other out. This positive area that I'm ignoring and this negative area that I'm including should cancel each other out. And so it certainly appears, using this midpoint Riemann sum, that this approximation is much closer to the true value of the area under this curve. What's difficult, though, is in our previous two examples, when I looked at the right Riemann sum, the right endpoint determined, and so I'm just squaring integers. When I looked at the left Riemann sum, my left endpoint determined, and I was just squaring integers. But when I'm looking at this midpoint, my midpoint are decimals, and so I'm squaring decimal values. And so although the area seems to have this canceling out effect, where I'm including area that I shouldn't, but I'm canceling it out with extra area that I'm ignoring, in reality this tends to be a little bit more work, because rather than dealing with these nice partition points, I'm actually dealing with these decimal points in between. And another thing that Riemann came up with is the idea that if I were to use more rectangles, I would get a better approximation. So I could take a look at this exact same curve, but instead of looking at this as 3 rectangles from 1, 2, and 3, if I were to do partitions at 2.5, at 1.5, and at 0.5, I could do midpoint approximations for each of these intervals. And the fact that I'm using more rectangles will actually allow me to get a much better answer, because the rectangles conform more to this curve. I still have area that I'm ignoring and area that I'm including that I shouldn't for each of these rectangles, but the fact that I'm using more rectangles, that gives me a more accurate approximation. Of course, we do end up with this ultimate trade-off. The thing is, I can have ease of use, but the thing is, if I have ease of use, then the trade-off here is less accuracy. If I do more rectangles, I end up with more accuracy, but I also end up with more work. So I can use this idea of area under the curve for very complicated shapes. I can kind of emulate what that shape would be by taking a collection of rectangles. And depending on my situation, maybe a left Riemann sum would be the best choice. Maybe a right Riemann sum would be the best choice. Maybe a midpoint Riemann sum would be the best choice. There are lots of different things that I could use here, and they each have their advantages and disadvantages. So I wanted to do one more function using a left sum, a right sum, and a midpoint sum. Let's say I've got y equals radical 9 minus x squared. Now I know that this is the top half of a circle, but if I look at it on the domain from 0 to 3, I've got a circle with radius 3 in this way. So if I do a left Riemann sum, that means I'm using my left endpoints to determine the height of each rectangle. And you can see in this case ends up being an underestimate as well, but just a slight underestimate, not nearly as much of an underestimate as it was before. Here, if I substitute x equals 0, my height is 3, and so my area is 3. Here, if I substitute a 1, my height ends up being radical 8, and my area is approximately 2.828. And here, if I substitute a 2, I'm going to have 9 minus 4, so my height is going to be 5, and this area is equal to radical 5. And when I find out the total area under the curve using this left Riemann Sum approximation, I end up with 8.064. Now, I know that this is an overestimate because I know that I am including area here, here, and here that is not part of the graph of the curve. I can also take a look at this exact same curve using a right Riemann sum. So if I look at y equals radical 9 minus x squared on my same domain from 0 to 3, this is the top quadrant of a circle. But using the right Riemann sums, now I'm using the right endpoints of each one of these intervals to determine the height of the rectangle. And you can see in this situation, I'm going to end up with an underestimate. Here, of course, when x equals 3, I end up with 9 minus 9, or 0. So the area of this rectangle is actually 0. The area of this rectangle is radical 8, and the area of this rectangle is the square root of 5. So my total area here is approximately 5.064. And I can tell here that this is an underestimate because there's area here that I am ignoring that should be part of my answer, but isn't. And I can tell that this right Riemann sum is probably not the best way to look at it because I am losing a whole bunch of area here and here. So let's investigate the midpoint Riemann sum for this situation. So if I take a look at y equals radical 9 minus x squared, the thing is, what's nice about the midpoint Riemann sum is that for every area that I'm including that I shouldn't, I'm also excluding area that should belong. And it looks like it should cancel out. So if this is my intervals 3, 2, and 1, I see that my midpoint is 0.5, and the height of this is going to be determined by 0.5 squared. 9 minus 0.5 squared would be 8.75. So my area here would be 8.75. For this one, if I look at this rectangle, my height is going to be 1.5 squared into this. So 9 minus 2.25 is 6.75. And so I see that I've got some area that I'm including, some area that I'm excluding, but this total area is 6.75. And when I look at this from 2 to 3, I'm going to take a look at 2.5. And my area is going to be determined by this height. And so if I take 9 minus 6.75, 9 minus 6.25, I've got 2.75. So the area of this rectangle is radical 8.75, radical 6.75, and radical 2.75. And so my total area in this situation is approximately 7.214. Now keep in mind that this lies between my underestimate of 5.064 and my overestimate of 8.064. But this is not saying that that's necessarily a better measurement. It certainly looks better because the area that I'm ignoring and the area that I'm including erroneously appear to cancel out. But it's not an exact answer here. And indeed, there are certain functions for which a midpoint Riemann sum is going to give you a less accurate answer. And also, because I'm dealing with a midpoint here, I'm dealing with numbers that are a lot more irregular. this radical 8.75 that comes from the 0.5 being squared, this radical 6.75 that comes from the 1.5 being squared, and this radical 2.75 that comes from the 2.5 being squared. This is a lot more work to do than in the previous problem. In the previous problems, I was taking the square root of integers, the square root of 8 and the square root of 5. Or in the case of our left Riemann sum, the square root of 9, the square root of 8, the square root of 5. So I notice that a midpoint Riemann sum is going to take more work. It doesn't necessarily give me a more accurate answer every time. And in our next lecture, we'll talk about some examples of when it doesn't. Another point that I want to make here is the difference between a left Riemann sum and a right Riemann sum is this left rectangle versus this right rectangle. Notice that this rectangle and this rectangle, my middle rectangles here, are the same for each of these. They're just translated one interval over. And that was true also of our y equals x squared. I had the area of 1 and the area of 5. It was this area of 9 that disappeared between my left Riemann sum and my right Riemann sum. These areas were here, but this area was not. So the difference between a left Riemann sum and the right Riemann sum is just that one rectangle on the left for a left Riemann sum versus the one rectangle on the right for a right Riemann sum. So there's lots of things to think about here, but the basic concept is, given a function, can we estimate the area under the curve using a left Riemann sum, a right Riemann sum, or a midpoint Riemann sum? Estimating the area under the curve using rectangles whose heights are determined by the function. And obviously, the more rectangles that I have, the more ways that I divide this interval, the more accurate my answer is, but at an expense that's going to take a lot more work to do so. If I use fewer rectangles, then of course it's going to take less work, but my answer is going to be much more off. I'm either going to have much more of an underestimate or much more of an overestimate. And the other thing to consider is that in this case, my left Riemann sum was an underestimate, but in the case of 9 minus x squared, my left Riemann sum was an overestimate. So the thing is, it's not the case where a left Riemann sum is always going to be an underestimate or always going to be an overestimate. It really does depend on how our function looks. It depends with whether or not we are increasing and decreasing. It also depends about the concavity. But those are things we're going to talk about in our next lecture. So this is Mr. Potter. Thank you for watching. Have a great day.